All right, so welcome to my series of video on statistics, and it's particularly exciting to be with you throughout this journey. And this happens to be one of the very important topics in statistics, which is usually used in research work. So this topic is actually about correlation and regression. But before this exciting journey, I would want you to like, subscribe, share, and most important, let us have your feedback. But more importantly, please subscribe to this channel. Now, in this video, I'm going to start by introducing you to correlation. All right. So I'm going to start by introducing you to correlation. Now, when we talk about correlation, okay, it comes from the word correlate. All right, so correlation comes from the word correlate. How two variables, they correlate with each other. Now, this simply means that correlation has nothing to do with causation. The fact that two things are related does not mean that one causes the other. So for instance, if two sets of quantitative variables are related, that if they have a positive relationship, it means that they move in the same direction. All right. If they have a positive relationship, it means that they move in the same direction. And if they have a negative relationship, it means that they move in the opposite direction. That is, if one is going to the right, the other will be going to the left. All right. The other will be going to the left. So that is a negative relationship. Now, one of the things I want you to know is that apart from calculating correlation coefficient, there is a graphical way of showing correlation. Let me give an example. Let's say we have a set of figures. Let's say we have a set of figures where we have figures X and Y. Let's say if X is 2, 4, 6, 8, 10. And let's say this is 5, 4, 3, 2, and 1. Now I can just draw a graph of Y and X. So I can just name here 2, 4, 6, 8, and 10. And then 2, 4, 6, 8, and 10. So you're going to plot these values. Now here, you realize that the observed value of X is 2 when Y is 5. Okay, so we have 2 against 5. We can plot it here. Then we have 4 against 4. We can plot it here. Then we have 6 against 3. So 6 against 3, we can plot it here. And then 8 against 2, we can plot it here. And then 1. And then 10 against 1, we can plot it here. So this is a clear example of a scatter diagram or a scatter plot. So a scatter diagram or a scatter plot is just plotting the two sets of variables on a graph. All right, that is a scatter plot. Now, if we use our intuition to check the relationship between these two sets of variables, what we realize is that these variables are negatively related. All right, these variables are negatively related in the sense that if you look at the direction of the various plots, it slopes downwards from left to right. That means that these variables are negatively related. But sometimes it is very difficult to tell the nature of correlation just using the scatter plots, okay? So then to give a more objective measure or to give a more reliable measure, we usually compute the correlation coefficient. We usually compute the correlation coefficient. So the nature of the formula for computing the correlation coefficient, almost all the time, you get correlation to be between -1 and +1. So if we have -1 and +1, and we have 0 in the middle, so what it means is that as the correlation coefficient approaches -1, it is becoming very strong and negative, right? It's becoming very strong negative. And once it's approaching +1, it is becoming very strong positive, all right? It is becoming very strong positive. And once it is 0, it means that there is no linear relationship between the two set of variables. Now, this is an example of a two-variable relationship as depicted by a scatter plot. So if you look at the one in plane A, all right, we could say there is a linear relationship between X and Y. But most importantly, because it slopes downwards from right to left, then we could say there is a positive relationship. Then if you look at plane B is a linear negative relationship because it slopes downwards from left to right, all right? But sorry, so the A, it slopes downwards from right to left, the A. Then the B, it slopes downwards from left to right, all right? It slopes downwards from left to right. Then in plane C, although we cannot see a clear linear relationship, the relationship more looks like a curve. So it is a curve and it is quite linear as well. So we call it curvilinear, all right? So that is a curvilinear negative. And then in plane D, we have curvilinear positive. Then in plane E, the nature of the plot is very difficult to tell. So plane E could be deemed as no relationship, and the same as plane F, all right? The same as plane F. So that is how we could use a scatter diagram to check. Now, as I mentioned, there is a more objective measure, all right? There is a more objective measure apart from the graph, and the objective measure is to use a formula, all right? So one of the formulas is that we can do it through deviations, all right? So it is sigma x. The first one is the correlation coefficient is equal to sigma into bracket x minus mean of x, another bracket y minus mean of y, all over the square root of sigma into bracket x minus the mean of x squared, then times sigma y minus the mean of y squared, right? So these formulas are in deviation form, okay? But we could also put it in the normal form. The normal form of this is when we have n sigma xy minus sigma x sigma y all over the square root of n sigma x squared minus sigma x all squared times n sigma y squared minus sigma y all squared. So that is an algebraic way of computing the correlation coefficient, which I believe is more objective than using the graph to determine. Now, this means that if we have a set of figures, we can just fix in the figures and then solve for the relationship. So if you look at this, we will need summation of xy, we will need summation of x squared, we will need summation of y squared. So here, if this was a question, we will just add xy as a column. Then we will add y squared and as well as x squared. So we add y squared as well as x squared. Then once we get our totals, we can get sigma y squared, we can get sigma x squared, we can get sigma x from this table, we can get sigma y from this table, and then we can get sigma x all squared, that is squaring this. Then we can also get sigma y all squared. So once you get these set of figures, it is easy to compute your correlation coefficient. Now, as I mentioned, the correlation coefficient ranges between -1 and +1. And one of the things you must realize is that the way the formula is designed, okay, it eliminates all the units of measurement. In other words, it is unit free, okay? The way the formula is designed in a way that it eliminates the unit of measurement. So any correctly computed correlation coefficient is unit free. All right, that means that it is not in cedis, it is not in dollars, it is not in meters, it is not in weight or kilograms, it is unit free. All right, so that is why we say it ranges between -1 and +1. Now, as I mentioned, the closer it is to -1, the stronger the negative relationship. And the closer it is to +1, the stronger the positive relationship. And the closer it is to 0, the weaker the relationship, whether it is negative or positive. All right. Then again, when it is +1, it is perfect positive relationship. And then when it is -1, it is perfect negative relationship. So that is how we interpret correlation coefficient. So here, this is a drawing, or this is a scatter diagram, which the data that was used to do the scatter diagram has also been used to compute the correlation coefficient. So in this plane, we see the scatter diagram, which is more subjective. Then we have an objective measure, which is the computed correlation coefficient. So in the first plane, we can see that this is a positive relationship. So the figures, when computed, it was +1. So because it is a very straight line. All right. Then the opposite is in plane 2, -1. Then in plane 3, we can see that it's some form of positive relationship, although it is not perfectly linear. That is why we have positive, but it is not +1. It's not perfect. It is 0.7. Then in plane 4 here, we have a negative relationship, although it is not perfect. So that is why we have -0.55. And then here, since there's no perfect relationship, since there's no discernible pattern in the relationship here, the computed correlation coefficient is 0. And then in the last one, there's a part that is negative. There's a part that is negative here. And there's a part that is positive here as well. So there's a part that is negative, and there's a part that is positive, and probably they cancel. That is why if you compute the correlation coefficient, the answer is 0. Now, there is also another example where the company is studying the relationship between sales and the number of years a salesperson has worked with the company. All right. So here we have 12 sales personnel. We took the number of years they have worked with the company, as well as the sales they have been able to generate. Now, once we plot a scatter diagram for the data, we realize that there is some form of positive relationship between them. That means that the number of years a person has worked, as well as the sales the person is making, moves in the same direction. All right, that is why it's a positive relationship. So this can also be done in Excel, and then we can compute the correlation coefficient using Excel. So there will be a series, or there's a series of my videos where Excel has been used to demonstrate all the statistical computations. Now let's come to significant testing for correlation. One of the things you must recognize is that when it comes to inferential statistics, okay, test of mean, test of proportion, hypothesis testing of mean, hypothesis testing of proportion, hypothesis testing of correlation, hypothesis testing of regression, etc. Once there is hypothesis testing, we are trying to infer from the sample to the population. All right, we always try to infer from the sample to the population. So this means that once we compute the correlation coefficient for a sample, okay, how can we be sure that that correlation coefficient is also significant for the population, or it is important for the population as well? Now, to do that, we are going to do hypothesis testing for correlation. Now, here, we make no distinction between a claim or a status quo or a research hypothesis. Here, the emphasis is that correlation by default, it has its own null and alternative hypothesis. All right. It has its own null and alternative hypothesis. Now here, what we need to recognize is that the null hypothesis is that the correlation is not significant. All right. Or in other words, we cannot generalize the correlation for the entire population. So the null hypothesis is that the correlation is equal to 0 or it is not significant. Then the alternative hypothesis is that correlation is not equal to 0 or it is significant. Now here, what we use to test correlation is T statistics. So here we don't use the Z, we use T statistics, all right? So here, the formula for the T statistics is the correlation coefficient, which is the R, divided by the square root of 1 minus the correlation coefficient squared over n minus 2, all right? Now, to compute the correlation, we must take note of these assumptions, all right? This statistical test works when both set of data are continuous or they are numerical, all right? Because the correlation we are discussing now is the product moment correlation, not the rank correlation. So here, our emphasis is on using numerical figures to compute the correlation coefficient. Then also, we must know that this formula works perfectly when we have two variables, two normally distributed variables, okay? Two bivariate normally distributed variables, right? So let's look at this example. So let's assume that the correlation coefficient is 0.8325. We are testing at 5% alpha or 95% confidence, all right? Then let's assume that the sample size is 12. Let's assume that the sample size is 12. So here the sample size is 12. And then we are testing at an alpha of this. So the sample size here is 12. Then the correlation coefficient is this figure. So if you fix them into the formula, it will be the R over the square root of 1 minus this R squared. So the R squared is the 0.6391 all over n minus 2. So 12 minus 2 is 10. So when you compute, the computed T or the observed T is 4.752. The observed T is 4.752. Now, I believe we understood how to read the T table from my video on confidence interval. So here, what we are going to do is that we are going to read, because correlation, the hypothesis is equal to and not equal to, that makes it two-tailed, all right? So we are going to read 95%, okay, 95% or 5% alpha with a degree of freedom of 10, okay, because for correlation, the degree of freedom is n minus 2, not n minus 1, all right? So with a degree of freedom of 10, 95% confidence, two-tailed. When you read, you are going to get a T value of 2.228. So if you plot this on the diagram, here will be negative 2.228, and here will be positive 2.228. Okay, so everything here is the acceptance region, and what is left is the rejection region. So the computed T is 4.752. So the computed T is 4.752, which is way outside. So it will be somewhere here, 4.752, which is way outside the acceptance region. So it means that we are going to reject the null hypothesis, all right? So we are going to reject the null hypothesis that there is no correlation and conclude that there is a significant correlation. So we will conclude using the alternative. So because we are testing correlation between years and company and sales volume, so we can say that based on the sample evidence, we conclude that there is a significant positive linear relationship between years with the company and the sales volume. All right, so that means that the correlation figure of 0.8325, although it is for the sample, that figure can also apply to the population. Okay, it is significant to the population as well. Right, it is significant to the population as well. That is how the computation is going to be. All right, so the steps here are specify the population of parameter of interest, formulate the null and alternative hypothesis, specify the level of significance, compute the correlation coefficient and the test statistic, construct the rejection region and the decision, and then reach a decision and draw a conclusion. So that is what we have done in this test. All right. So it has been good to have you. And then my next video will be on regression. So please subscribe, share, comment, let us have your feedback, and more importantly, subscribe. So the next video is going to be on regression analysis. Thank you.